Hi everyone, I'm Jane from Group 13 SSCM 3423 Numerical 2 Section 1. In this video, we will use the finite difference method to solve linear equation with the Robin boundary condition. And these are my group members, Huishen, Fitri Shahira, Fiuza Madiha, Azmi Pat, and Ariel Rizman.
Good day everyone. Before we begin, let us look at the learning objectives of this presentation. By the end of this presentation, students should be able to explain the concept of a linear boundary value problem and understand the meaning of Robin boundary conditions. Next, students will learn how the finite difference methods is applied to approximate the solution of a differential equation. Finally, students should be able to understand how the resulting system of linear equations can be solved using the Thomas algorithm. So now we move into our introduction. A boundary value problem involves a differential equation together with conditions specified at the boundaries of an interval. In these slides, we focus on a linear second-order boundary value problem with Robin boundary conditions. The finite difference method is used to convert the differential equation into a system of algebraic equations by replacing derivative with numerical approximations. This method is useful when finding an exact analytical solution is difficult or impractical.
Now, let's look at the actual mathematical formulas we use to make this substitution. To approximate the first derivative y prime at an interior node yi, we implement the standard 3-point centered difference formula. This formula estimates the slope at the current node by taking the value of the forward node yi plus 1, subtracting the value of the backward node yi minus 1, and dividing the result by 2 times the step size, which is 2h. This centered approach provides a well-balanced, second-order accurate approximation of the local rate of change. Similarly, to handle the second derivative y double prime, we use the 3-point centered difference formula for second derivatives. The approximation at our interior node yi is expressed as yi minus 1 minus 2yi plus yi plus 1, all divided by our step size squared or h squared. This formula links our central node directly to both its immediate left and right neighbors. When we take these two difference approximations and substitute them directly back into our general second-order differential equation, we get our interior node master equation. By applying this exact master equation systematically to every single interior node along our grid, we transform the continuous differential equation into a structured system of simultaneous linear algebraic equation. Once we incorporate our boundary condition, such as the Robin boundary conditions where values and flux interact, we get a closed, complete system of equations that can be efficiently solved using algorithms like the Thomas algorithm. This moves us seamlessly from abstract calculus to an exact computational numerical solution. Let's explore the type of boundary condition we might encounter. The first and most straightforward type is the Dirichlet boundary condition. Under a Dirichlet condition, we are given the exact value of our function at the boundary. Mathematically, this is written simply as y at a given boundary points equals a non-constant, which is alpha. In physical terms, if you are modeling heat distribution along a road, a Dirichlet condition means you are fixing the ends at a constant, non-temperature. Computationally, this makes our life much easier because the boundary value is already a non-constant. We don't need to approximate a derivative at this point. We can directly substitute this constant into our neighboring interior equation, which effectively reduces the number of unknowns in our linear system. The second major type of boundary condition is the Newman boundary condition. Unlike Dirichlet, which specifies a fixed value, a Newman condition specifies a fixed gradient or rate of change at the boundary. Mathematically, it involves the first derivative written as y prime equals to a constant. In a physical application like thermodynamics, a Newman condition represents specified heat flux. For instance, an insulated boundary where heat cannot escape would have a derivative of 0. When applying the finite difference method, Newman conditions require an extra step. Because the boundary value itself is unknown, we must use a finite difference formula to approximate the derivative at the boundary node. This process introduced an imaginary node outside our grid, known as a ghost point or ghost node. We then combine our boundary equation with our interior master equation to eliminate this ghost node, allowing us to successfully build and close our final tridiagonal matrix.
Now move on to the steps. Let's begin with step 1, where our goal is to evaluate our standard Center finite difference equation right at the very first node on our grid, the left boundary where our index I equal to 0. Now, look closely at what happens when we mathematically write out this approximation. In our second derivative term on the left, a serious structural problem emerges, which you can see circled in red on the slide. The term 1 negative 1 appears. Because our physical grid and our interval domain strictly begin at x at 0, this point y negative 1 represents a value that exists entirely outside our defined boundary. In numerical analysis, we call this an imaginary or ghost node. It is completely unquantifiable on its own, which means our system is currently blocked. We cannot solve our matrix until we find a legitimate mathematical way to define or eliminate this ghost node. To overcome this hurdle, we move to step 2. Since the ghost node originates because of a boundary limitation, we look directly to our boundary condition for the solution. In this problem, we are given a Newman boundary condition at the left boundary. This tells us that the derivative of y with respect to x at our starting point at 0 is equal to a non-constant value, which we denote here as lambda. To make this boundary condition useful for our discrete grid, we approximate the first derivative using a centered difference formula. This gives us the expression y1 minus y negative 1 over 2h equal to lambda. Why do we use a centered difference here instead of forward difference? Because it maintains a higher order of accuracy. From here, we use straightforward algebra to isolate our ghost node, y negative 1 equal to y1 minus 2h lambda. Moving on to step 3. We substitute this ghost node expression straight back into our original governing ODE. If you look at the two red circles highlighted on the slide, you can see the exact points of entry. We take our expression, y1 minus 2h lambda, and carefully plug in into the equation whenever y negative 1 used to sit. First, into the numerator of our second derivative approximation on the far left, and second, inside the first derivative approximation multiplied by our coefficient function ps0 on the right. The profound takeaway of this step is that by performing the substitution, the ghost node completely vanished from our system. It is entirely replaced by valid internal grid points and known boundary parameters. To step 4, where we pause to simplify the algebra on both sides. So on the left hand side, we represent our second derivative. We distribute the sign and combine our like terms. The two separate y1 terms combine, condensing the numerator into 2y1 minus 2y0 minus 2h lambda over h square. Simultaneously, let's look at the first derivative inside the parentheses on the right hand side. Here, the positive y1 and the negative y1 cancel each other out entirely. This leaves us with just 2h lambda and 2h lambda over 2h, which simplifies perfectly down to just lambda. When we reassemble this individual piece back into our full equation alongside our qs0, y0 and rs0 terms, we are left with a vastly simplified equation. On step 5, we separate our unknowns from our knowns. We first multiply the entire expression by h square, the denominator, and remove the fraction completely. Once the fractions are gone, we rearrange our terms into two strict groups. We shift all of our unknown grid values, which are the variables we are actually trying to solve for, namely our y0 and y1 terms, over to the left hand side. On the other side of the equal sign, we group all of our known values, our step size h and our boundary constant lambda and our function coefficient p, q and r. By structuring the final equation this way, we have achieved three critical things. We have successfully integrated the Newman boundary condition, completely eliminate the out-of-bound ghost node, and format this specific boundary row so it can be inserted directly into our tridiagonal linear system matrix.
Okay, now, to better understand how these concepts are applied in practice, let us solve a worked example using the finite difference method for linear Robin boundary condition problem. The boundary value problem is y double prime equal to y plus x. The Robin boundary conditions are y0 plus y prime 0 equal to 0.5 and y1 minus y prime 1 equal to 0. And the step size h is equal to 0.25. Next, the first step is to divide the interval from 0 to 1. And since h is equal to 0.25, we get 5 grid points, which are x0 equal to 0, x1 equal to 0.25, x2 equal to 0.5, x3 equal to 0.275, and x4 equal to 1. And at these grid points, the values of y are unknown. Therefore, we need to find the unknowns y, which are y0, y1, y2, y3, and y4. Okay, next, we derive the final difference equation. We use the three 3-point center difference formula for the second derivative yi double prime equal to yi minus 1 minus 2yi plus yi plus 1 over h squared. And then we substitute this into the equation of y double prime equal to y plus x. Then we will get the equation of yi minus 1 minus 2yi plus yi plus 1 over h squared equal to yi plus xi. And then we multiply both sides by h squared. We will get the equation of yi minus 1 minus 2yi plus yi plus 1 equal to h squared yi plus h squared xi. And next, we rearrange the yi terms so that the equation will become like this. And since h equal to 0.25 and h squared equal to 0.0625, the final difference equation becomes like yi minus 1 minus 2.0625 yi plus 1 equal to 0.0625 xi. And these equations will be used to form the system of equations. Okay, now we apply the first boundary condition. The given condition is y0 plus y prime 0 equal to 0.5. And these conditions can be written as y sub 0 plus y prime sub 0 equal to 0.5. To approximate the derivative, we use the 3-point center difference formula, which is y prime I equal to yi plus 1 minus yi minus 1 over 2h. So we will get y prime 0 equal to y1 minus y negative 1 over 2h. And then we substitute this into y0 plus y prime 0 equal to 0.5, so that we will get the equation of y0 plus y1 minus y negative 1 over 2h equal to 0.5. And then we multiply both sides by 2h. We will get 2h y0 plus y1 minus y negative 1 equal to h. And then we rearrange to make y negative 1 becomes a subject. So y negative 1 equal to 2h y0 plus y1 minus h. Since h equal to 0.25, and we will get y negative 1 equal to 0.5 y0 plus y1 minus 0.25. These equations allow us to eliminate the ghost point, which is y negative 1, since it is outside the interval. And next, we apply the second boundary condition. The given condition is y1 minus 2y prime 1 equal to 0. And this condition can be written as y4 minus 2y prime 4 equal to 0. And we use the 3-point center difference formula, which is y prime I equal to yi plus 1 minus yi minus 1 over 2h. And y prime 4 equal to y5 minus y3 over 2h. And then we substitute this into the boundary conditions, and we will get y4 minus 2y5 minus y3 over 2h equal to 0. Since 2 can be cancelled out and we multiply h, we will get hy4 minus y5 plus y3 equal to 0. We rearrange to make y5 become the subject. So y5 equal to hy4 plus y3. Since h equal to 0.25, and we obtain the equations y5 equal to 0.25 y4 plus y3. And this equation allows us to eliminate the ghost point y5 since it is out of the interval.
Next, we move to step 5, which is building the system of equations. Using the master equation to find the solution of yi, where I equal to 0, 1, 2, 3, and 4. For I equal to 0, we substitute the boundary relation obtained from step 3, which is the first Robin boundary condition. After substituting y minus 1 into the master equation and simplifying, we obtain negative 1.5625 y0 plus 2y1 equal to 0.25. This becomes our first equations. Next, for I equal to 1, we substitute x1 equal to 0.25. We obtain y0 minus 2.0625 y1 plus y2 equal to 0.0156. Next, we continue applying the master equation to the remaining interior nodes. For I equal to 2, where x2 equal to 0.5, we obtain y1 minus 2.0625 y2 plus y3 equal to 0.0313. For I equal to 3, where x3 equal to 0.75, we obtain y2 minus 2.0625 y3 plus y4 equal to 0.0469. And finally, for I equal to 4, we use the second Robin boundary condition derived in step 4. Substituting y5 equal to 0.25 y4 plus y3 into the master equation and simplifying gives 2y3 minus 1.8125 y4 equal to 0.0625. Therefore, all 5 equations are obtained and can now be written in matrix form and solved using the Thomas algorithm in the next step.
Hi, Next, I will be presenting a step-by-step of how to solve a system of linear equation using Thomas' algorithm. As you can see on the slide, our general tridiagonal system is represented by the variable ci for the lower diagonal, di for the main diagonal, and ei for the upper diagonal. Y represents our vector of unknowns, and lastly, d is our right-hand side constant vector. For our specific problem, we have this matrix system. Our main diagonal values, d, we have d1 equal to negative 1.5625, d2, d3, and d4, we have negative 2.0625, and d5, we have negative 1.8125. For the upper diagonal e, e1 we have 2, e2, e3, and e4 we have 1. For the lower diagonal c, for c2 we have 1, c3 and c4 we have 1 also. For the c5 we have 2. For the b, we have b1 equal to 0.25, b2 equal to 0.0156, b3 equal to 0.0313, b4 equal to 0.0469, and lastly b5 we have 0.0625. Let's look at how we can systematically solve the unknowns y1 through y5 using the algorithm's two core phases, which is the forward elimination and the backward substitution. Okay, we begin first with the forward elimination phase. The goal here is to transform our tridiagonal system into an upper bidiagonal system. To do this, we calculate three new sets of parameters sequentially from I equal to 1 to I equal to 5, which are for alpha I, beta I, and wi. Let's walk through the calculation. For I equal to 1, alpha 1 is simply equal to our first diagonal element d1, which is negative 1.5625. Using this, we can find beta 1 by dividing e1 by alpha 1 and giving us negative 1.28. Finally, W1 is D1 divided by alpha 1, resulting in negative 0.16. For I equal to 2, we update our diagonal to find alpha 2 using the formula alpha I equal to di minus ci times beta I minus 1, and giving us negative 0.7825. So we repeat the process to find beta 2, which is negative 1.2780. For W2, we have negative 0.2244. For I equal to 1 and 4, we follow the exact same rhythm. Alpha 3 is calculated as the negative 0.7845. Beta 3, we have negative 1.2747. And W3, we get negative 0.3259. For step 4, alpha 4 becomes negative 0.7878. Beta 4 equal to negative 1.2694. And W4, we have negative 0.4732. Finally, for I equal to 5, since this is our last row, we need to compute only alpha 5 and W5. Alpha 5, we get 0.7263, and W3, we get 1.3891. Because this is the end of forward step, our final unknown Y5 is exactly equal to W5. So we already have found our first answer, W5 equal to 1.3891. So now we have successfully completed the forward step and we found Y5. So we can move on to the second phase, which is backward substitution. In this step, we work backward from I equal to 4 down to I equal to 1 using the formula yi equal to wi minus beta I times yi plus 1. So let's plug the number we just calculated to find y4. We take w4, which is negative 0.4732, and subtract the product of beta 4 and y5. This gives us 1.2901. So to find y3, we use w3, beta 3, and our newly found y4. So the calculation giving us 1.3186. For y equal to 2, we substitute backward again using y3, and we get 1.4608. Finally, for y1, we use W1, beta 1, and Y2, and giving us 1.7098. To summarize our final solution for this matrix system, we get y0 equal to y1 equal to 1.7098. For y1 equal to y2 equal to 1.4608. For y2 equal to y3, we get 1.3186. For y3 equal to y4, we get 1.2901. And lastly, y4 equal to y5, we get 1.3891.
In conclusion, the finite difference method is a useful numerical method for solving linear boundary value problems with Robin boundary conditions. As in our example, we applied the finite difference formula and used the Robin boundary conditions to form a system of linear equations. And then, the system was solved using the Thomas algorithm. From our calculation, the approximate values we obtain are y0 equals 1.7098, y1 equals 1.4608, y2 equals 1.3186, y3 equals 1.2901, and then y4 equals 1.3891. Therefore, this method provides a practical way to approximate solutions for problems involving both function values and derivatives at the boundaries. So that's all from our group. Thank you very much.